Hi, my name is George Phillips. I'm the SU at WFO Topeka, Kansas. I'm going to be giving a presentation on storm motion and drawing polygons. And the main purpose of this is to improve polygons and minimize false alarm counties. This presentation was given as part of our severe weather seminar here in Topeka, Kansas, and in preparation for the impact-based warning project that's upcoming for offices in Missouri and parts of Kansas. The outline of the talk is going to include looking at pure storm-based warnings, which began in October 2007, and talk about some of the challenges and potential issues associated with that. We'll be looking at meteorological and non-meteorological factors in polygonology, and looking at methods to improve warning polygons, both meteorological and non-meteorological. As part of the meteorological part, we're going to review the Bunker's ID method, internal dynamics method, for estimating supercell motion, and talk about some of the inherent limitations of that method. We'll go through an example where it worked very well in an isolated storm, and some examples where it didn't work as well due to non-internal dynamics propagation and some other issues. And then finally, we'll look at a suggested methodology in WarnGen to minimize the needlessly warned areas. So pure polygonology, or pure storm-based warnings, like I said, that the storm-based warnings really started in October of 2007. And in the past, some have suggested that we should be turning off our map backgrounds when we're drawing our polygons and not be concerned with geographic boundaries. Meteorologically, that makes sense. It also means that specific locations aren't underserved by always getting the shortest lead time. So if you live on the west edge of a county in a county warning area where people cut their polygons off at the county borders, you know that you typically get the lowest lead time as the polygons are then issued downstream. And it also works great if everyone is warned through latitude and longitude. But the realities of pure storm-based warnings are that many alert systems are still county-based. Siren systems in some counties are this way, where you set it off for one, it goes off for everyone in the county. Some software apps key on the UGC as opposed to the latitude and longitude. And of course, no weather radio goes off by county. Many warning display systems are still county-based, even if it's not an alerting system. For example, some web displays just show the counties where the severe thunderstorm or tornado warning are in effect. TV warning bug maps, a lot of those just show the counties highlighted in a certain color based on what kind of warning's in effect. And there are others out there as well. So if we ignore political boundaries frequently, many people are effectively being alerted too much, because they are being warned by county. As part of the impact-based warning project, Ken Cook, who's the SU at Wichita, produced a graphic here of counties in severe thunderstorm warnings for each one of the offices in the project by year. So it goes from 2000 to 2011, and you can see from 2000 to 2007 there really wasn't much of a trend. It was pretty up and down by year, but pretty basically steady as you go through all those years in terms of the number of counties and severes. And then in 2008, of course, that was the first year, our first full year of storm-based warnings, we immediately saw an increase in counties warned and severes. And although it's gone up and down since then, you can see that it's averaged out to be well above what it was prior to 2008. Another graphic from Ken that shows counties in tornado warnings by year by office. Once again shows that there were up and downs from 2000 to 2007, with 2006 being a big year. But overall, since 2008, we have more counties in tornado warnings per year. This table was also produced out of that spreadsheet. And just looking at Topeka in that list, you can see in the first column here, the average counties warned from 2000 to 2007 was 361. This includes both tornado and severe thunderstorm. And then the average counties warned from 2008 to 2011 was 621. So That's 172% of the 2000 to 2007 number. The severe change was the biggest part of that with 176% and a lot more warnings, obviously. And the TOR change went up, basically was 137% of the 2000 to 2007 counties. So you can see both of them increased on average after we went to storm-based warnings in fall of 2007. Now he also includes on here the average from, or the number from 1986 to 2007, the average, and then the comparison there. But there was a lot of change in the way we did business in the late 80s and early 90s, and so it's kind of a different type of comparison there. But what we can see is that things went up pretty immediately and stayed steady after the advent of storm-based warnings. I shared this presentation with a forecaster in an adjacent office. It's not in the project, and he wanted to look at what went on for his county warning area. And what he did here is plot the number of counties per warning for each one of those years. In this case, 2000's over here, from 2000 to 2011. And you can see that from 2000 to 2007, the vast majority of warnings that only had one county associated with them, and nearly all were either one or two county warnings, with very few with three or more. But since 2008, there are actually as many, if not more, 2 and 3 county warnings as there are 1 county warnings. So you can see a different way of looking at it, but obviously since storm-based warnings, we haven't been worried about counties as much, and it shows up in the way that the statistics are falling out from this office. So the reasons for the increase, part of it could be chance. We could just be more active with messier storms and more squall lines and whatever since that time, but since the increase was immediate in 2008 and sustained, that doesn't seem very likely. The influence of pure storm-based warning ideas in training, where you clip small parts of counties and don't worry about county borders, certainly that's had some effect on it. You can no longer enlarge a polygon for an SVS. Prior to 2008, if you issued a warning for a county and or some parts of 2 counties and the storm started moving out the right side of that polygon, you could simply enlarge the polygon for the SVS, encompass it in that follow-up statement, and not have to reissue a warning for the threat. Now, with pure storm-based warnings, you can't do that. And so if you do have a storm moving out of the initial polygon, you have to issue another one to either replace or add on to the other polygon, which may include 1 or more counties. The other thing trying to mitigate that problem would be that some people draw larger initial polygons. Given the uncertainty and not wanting to do this, people may draw larger polygons, resulting in more counties per warning, and that means that you may not have to reissue a polygon if the threat moves out of what might have been in this polygon. So you're covering uncertainty there and may lead to more counties warned. The motivation for the impact-based warning experiment is that warning fatigue can occur if people are alerted frequently and nothing of significance happens nearby. In this presentation, we'll look at attempting to reduce the number of times a county is warned by improving the initial and follow-on polygons so rewarning is less frequent, and minimizing counties that are just clipped by polygons where the threat is minimal. One way to look at this, and an example of this, was part of a presentation given by Daryl Hertzman of Iowa State IEM cow fame that he did at the 2011 NWA conference in Des Moines. The discussion of this part of his presentation centered on pure storm-based warning polygons versus the fact that some systems are still being alerted by county. So what we have here is a radar picture with no county maps overlaid of a supercell storm that's been steady state moving to the east-northeast, and is pretty easy to track. And this arrow, this white line, shows the past track and the extrapolation 45 minutes or 30 minutes into the future. Now, with WarnGen, not worrying about counties, we just pop up a warning polygon, and in the ideal world, these storms are steady state, and their pure extrapolation works well. We just draw our initial polygon where we widen it as it goes out in time to factor in some uncertainty as you go out there, and it's pretty easy, and you can issue the warning quickly. So if I do that and just draw up the polygon, or let it do its extrapolation and have the default WarnGen polygon, then I draw the too far end back to the tip of the extrapolation arrow. Here's my polygon, and I'm done at this point, right? I don't really need to do any more. But if you look at what that affects, you have 5 counties that are clipped by this polygon. There's one because of the way WarnGen does the back end of the polygon, well behind the dot, or where you're tracking the storm. You have a county that's not threatened in the least by this storm behind it. You have 2 counties that are well downstream at the end of the warning that may or may not be affected by this storm and has a low probability of being affected by the tornado, at least during the tenure of this warning here. So people in these other counties, if we just left the default polygon up there, could be alerted by weather radio or maybe even a siren going off in their community simply based on the fact that the polygons touch their county. So what we tend to do, and probably should do in these cases, is get rid of this county with Guthrie Center in for sure, and worry about these later on if the storm starts turning to the northeast or whatever, or continues downstream. This county with Nevada in may need to be warned later on. But this initial warning, which covers the threat out into 30 minutes into the future, now encompasses only 2 counties, the ones most likely to be threatened during that time frame. So now Daryl says he can stay asleep, at least for now. So we have these idealized polygons for steady state storms that we just issue out in time based purely on meteorology, and that's nice, and I wish we could do that, but we do have to factor in political borders sometimes, or these needless alertings occur quite frequently. I'm going to now talk about the meteorological and non-meteorological factors in drawing our polygons. And when we're talking about meteorological factors, you really have to ask, is pure extrapolation appropriate? That's what we come up with a default warning polygon, WarnGen, and sometimes it's perfectly appropriate because the storm is steady state, it's been doing the same thing for a long period of time, and we expect it to continue into the future that way. But a lot of times it's much more complicated than that. A lot of times we're drawing our severe thunderstorm warnings for a strengthening storm in a sheared environment and it's moving in one direction. And we know that as it organizes, it's going to probably turn to the right or left and move in a different direction. We have to factor that in. It's a forecast we're making when we're drawing these polygons. If a storm is developing along or near a boundary, propagation is affected by that boundary, and we must consider how that boundary might affect the storm movement and draw our polygons to include that uncertainty. Is the storm accelerating or slowing down? Are we going to have mergers of various types that could factor into where the threat moves with the storm that we're warning on? Splitting storms can create complications, and there's different ways to handle that. These are all meteorological factors. And we could be warning on a storm that appears to be in one environment, and then the environment can change rapidly, and the storm motion can also change rapidly. So we're looking at all these things when we're thinking about meteorological factors when we're drawing our polygon, or we should be at least very aware of these things when we're doing this. Now there's the other customer factors that we also have to be concerned with. We've already talked about people are being alerted by county, or a lot of them are. And we also have to worry about if we're doing pure storm-based warnings, we have multiple storms and they're messy, and what happens if we issue pure storm-based warnings and we have 3 or 4 warnings for the same county? What kind of message are the people in that county hearing? How are the media handling that or trying to explain that? We also have population centers and the associated potentially larger impacts, which sometimes come into play in how we draw our polygons into whether we warn for an entire metropolitan area or not, and that's really the fourth bullet as well. Metropolitan areas often come with their own set of complicating factors. So, you have all these meteorological factors that you have to keep track of and think about, and you also have the customer factor. So it's not an easy process a lot of times. This is kind of a exercise that we're going to go through, and just kind of showing how complex it can be, factoring in both meteorological and non-meteorological factors when we're drawing our polygons. This is taken from a presentation given by Kevin Scharfenberg at the Denver 2010 Conference on Severe Local Storms. And on the following slides, we're going to look at an environment, radar time sequence, forecast, meteorological evolution, uncertainty, and potential customer impacts, and try to come up with a warning polygon. So we've already seen this, and once again, this looks pretty simple over here, following steady state storms out into time, not worrying about anything but the storm itself. The environment we're going to be looking at for the storms is given by this sounding and hodograph. And you have 3,600 joules per kilogram of CAPE. Very nice thermodynamic diagram there. Hodograph is even more impressive with large clockwise curvature in the lowest 3 to 4 kilometers, with deep shear through quite a layer here beyond that. You have storm relative velocity in surface to 1 kilometer, 460, surface to 3 kilometers, 710, etc. Deep layer shear, significant of surface to 6 kilometer of 77 knots. So considerable shear in the environment, a lot of low-level turning. A very impressive supercell and potentially tornadic sounding. If we look at the radar picture at this time, there's a dry line out here, and we have storms developing just east of the dry line. Strongest storm is this one, and we have a couple others just to the north that look pretty intense, especially this one. We also have other cells just starting to form along the dry line at this point. Extrapolation of the strongest storm, which appears now to be severe, takes it to the northeast or east-northeast at 45 minutes out into this point here. If we draw up the default polygon and draw the far end back towards the tip of the extrapolation arrow, we have a polygon ready for this storm now based on pure extrapolation. Are we done at this point? Well, we have to factor in meteorological factors, and we know it's a supercell environment, and this is rapidly strengthening. And so we might want to draw the right side of the polygon down to the right to take into account the fact this thing may be curving. Now it's starting to rotate, curving more to the right. We also have this storm here that looks like it's almost severe and has been intensifying. And we may want to cover this as part of the initial warning as well. We also see kind of a tight gradient on the north side of this storm, and we see anticyclonic rotation aloft, possibly a splitting storm. Now, the environment for this split was not very good with this large clockwise curved hodograph in low levels, but in some cases you have to be worried about that as well. In this case, probably not. So now we've covered these storms out here. Are we done at this point, or is there anything else we should factor in meteorologically? Well, what if I told you that this cell here, which looks like basically nothing at the surface, has 60 dBz at 25,000 feet, is it intensifying as well? It's moving to the northeast. Well, it could move into this polygon before it gets severe, and that's probably the case, but if you weren't certain, you might enlarge your polygon a little bit more. And we also see this storm is also intensifying aloft, and, well, we can draw it down there too. Now, it's getting kind of ridiculous, but I'm just showing some of the things that, even if you're not going to draw the polygon for, you should be considering when you're thinking and forecasting what the evolution of these cluster of storms is going to be later on. And if this storm develops rapidly and turns right because of the environment, you could have a polygon that looks like this, which is huge. And now we know that downstream, the far edge of the polygon basically bisects Norman and Oklahoma City. And let's say that the city managers or the county Emergency managers don't like to have their metropolitan areas split, and they'd like to have either none of the metropolitan area in the warning or all of the metropolitan area in the warning. So you're taking into account a customer factor, which we wouldn't want to take into account, but sometimes that happens. And so you could have a warning that looks something like this based on that. Getting huge now. And if we were to do that, we'd have to go to an hour warning, because there's no way in 45 minutes any of these storms are going to get to the eastern side of this polygon. So this is kind of ridiculous. You should be thinking about all these things, but don't necessarily draw a polygon that encompasses everything. So there's multiple ways of looking at this. And here on this slide are the ways we can look at it, or at least a few of them we can look at it. This is the one we looked at on the previous slide, which is huge. And then down here, we have the one that is most pure storm based, in the lower right, number 4. We have a warning for this storm that looks severe, this one, which is severe now. And then maybe further on downstream, when we have more certainty about what these other storms are going to do, we draw follow-on polygons. Well, this is the most pure storm based, but it also has 5 warnings that intersect Cleveland County. So what are we giving with that type of message? So maybe the best solution is somewhere in between with one of these two here, where we have fewer, or we have more than one initial polygon it's huge here, and then as we gain certainty as to how these other storms are going to evolve, we have more warnings downstream. Not trying to cover everything in one warning, but not trying to do pure storm base, which is also maybe perhaps creating problems with the sheer number of warnings that we're issuing for a given county. So the summary of that is you're drawing these polygons using meteorological reasoning and non-meteorological factors. Obviously, anybody who's done this in complicated environments knows that it's very challenging at times, and that no two people may handle the same situation the same way. And there's no real easy answer. One has to factor in both of those considerations. You're trying to balance customer impacts, uncertainty, workload, and our ability to forecast an hour into the future when we're drawing these polygons. It's a very challenging thing. How can we decrease the sheer number of warnings and associated alerts? One way we can do that is through better initial and follow-on polygons. And I say duh here because that should be obvious. We try to do the best we can, but I think we can do better. We can do better for both severes and tors. How often do we see someone having to reissue a polygon for the same storm or cluster of storms within 15 to 20 minutes of your warning issuance? Especially for severes, but how often does that occur? And the answer is too often. Sometimes things are unforeseen, and it's almost impossible to foresee that occurring, and you couldn't help it. But there are other times that we can obviously do better when we have to be thinking about why this occurred and how we could have done better in each one of those cases. If we do have fewer such warnings, we can decrease that customer confusion if we have multiple warnings for the same county, and perhaps warning fatigue if we have multiple alerts that we could have just handled with one alert. So that also, as importantly for me, is it decreases our workload in the office and frustration level. We don't have to keep track of as many warnings. We don't have orphan polygons sitting out there that we're afraid to cancel because we might confuse someone, but we've replaced it with another polygon, and having to worry about taking something off a no weather radio because it's been replaced or no longer in effect, but we can't cancel it through an SVS because of fear of confusion. So if we can draw better polygons, more intelligent polygons, we can decrease our workload and frustration. Another way is this county clipping. We talked about that already in that exercise from Iowa. How often is a county included as just clipped by a polygon? And how often is that small area of the county truly threatened by something significant during the duration of the warning? Now, absolutely, sometimes that small clipping is necessary. You got a supercell with a hook moving. It looks like it's going to move near or across the northwest corner of a county. You don't want to play with fire in that case and not include that county if it turns more right or whatever. You want to include that. But sometimes we can have a situation where we have a tornado warning that's encompassing an entire supercell, and the far northern part of that warning may have some inch-size hail in it, but it's just clipping the southeast corner of the county. And how often, what's the impact of us issuing a tornado warning for 1-inch hail because we're encompassing the entire supercell with that tornado warning? So maybe in that case you can not have that southeast corner of the county included. A way to increase or improve on the initial polygon and follow-on polygons for supercells is to understand the bunker's internal dynamic supercell motion. The training and articles are listed down on this slide. The initial article from 2007 in Weather and Forecasting was really described the technique for isolated supercells predicting motion in advance, and this technique worked better than anything that had previously come out and is utilized in many software applications and hopefully by all warning forecasters when they're warning for supercells. Zeitler and Bunkers in 2005 and NWA Digest produced a more extensive paper that gave more examples and also more examples of where it doesn't work very well, or where the limitations of the method for isolated storms just don't work because of additional propagation problems. And Matt Bunkers then developed a visit view training session based on that paper that's available can be played back teletraining wise on the web, and is an excellent review of that method and its limitations. But I'm going to go through very briefly here, just as a brief review, the method, and then give an example of where it works, and then talk about the limitations and where maybe we need to understand that it doesn't work. The strengths are that it works well for isolated supercell storms frequently. It gives a decent estimate of eventual storm motion for intensifying storms in a sheared environment. So obviously that has potential positive warn gen implications, and you should have the Bunkers ID method supercell estimates on your warn gen pane to help with your orienting polygons. We warn a lot of times for storms that are just intensifying and not rotating, not really organized at the point we're warning for them. But we have to figure out what it's going to look like 30, 45 minutes in advance. And looking at it in a sheared environment, we can use Bunkers to give us an idea of how to enlarge a polygon and encompass that storm. And it's a decent estimate for use in calculating storm relative environmental parameters before the storms develop. Now the limitations for the default ID motion calculations, if you don't have isolated supercells, it's not as good. Interactions of the storms with boundaries, merging storms, interactions with topography affect propagation, and that's not internal dynamic propagation, it's a different type of propagation, and so it's not really designed to handle those situations. And also, complications can result from the statistical background. Although it's physically based method, the results fell out of statistics, looking at a large number of supercells, and those storms and environments that fell outside the mean, fell well outside the mean, may result in motions that we don't expect. Non-standard shear profiles, shallow storms, elevated storms don't necessarily fit or aren't in the database in a large enough manner that the average method for calculating the storm motion works really well for those. So the classic ID Bunkers method, isolated supercell with perturbation pressure gradient forces, enhance updraft on the flanks of the initial updraft. It results in perhaps splitting storms, and you have propagation to the right or left of the mean wind. And here's a classic Klemp diagram where you have time A here, developing storm in a sheared environment. The updraft tilts the horizontal vortex lines into the vertical, stretching increases the vorticity in the mid-levels of the storm. That creates upward directed perturbation pressure gradient forces on the flanks of the initial updraft. that results in updraft strengthening on the flanks of the initial updraft and propagation to the right and to the left of the shear vector, and a splitting storm in this case. And looking at how the bunker's ID method of storm motion is then calculated, you have a near surface wind and a mid-level wind, in this case 5 kilometers. You draw your bulk shear vector between the two winds. You have a mean wind calculated with a tip up here. Your propagation vectors due to internal dynamics would be to the perpendicular to the left and to the right of this bulk shear vector, and doing the calculation for the right moving and left moving supercells, you have the mean wind and you draw perpendicular to the bulk shear vector 7.5 meters per second to the right for the right mover, and your resultant storm motion is there, and 7.5 meters per second to the left of the mean wind tip, perpendicular to the shear vector for your left mover. And so there you have it. It's probably a little more easily explained in a true hodograph here, where you have your mean wind, the tip of your mean wind vector right here is a square gray dot. And your typical hodograph through 10 kilometers here, you draw the 0.5 to 5.5 kilometer bulk shear vector here, and then through perpendicular to your bulk shear vector, 7.5 meters per second to the left, 7.5 meters per second to the right of the tip of your mean wind vector, and that's your left mover and your right mover for the supercell. An example of where it worked well was 28 February 2007. We had a warm front moving slowly north across east central Kansas, which is the southeastern part of our county warning area. The storms developed in the warm sector to the south of the warm front. We had straight line hodographs in that environment, which resulted in initial splitting storms. The ID method did a great job of predicting the right mover and a pretty good job at forecasting the left mover, which was not as well organized. And the right mover ended up having an EF2 tornado in our southeasternmost county, which went on to produce an EF4 in Pleasant Hills area. The radar loop we're going to look at quickly is from 2335Z to 0122Z on 1 March. So basically a 2-hour time period here. And on the radar, we also have the right mover and left mover from the RUC 40 overlaid with the right mover in cyan and the left mover in yellow. So here's the cluster of storms down over east central Kansas, which had been moving northeast given this extrapolation here. And the initial warnings that we put out for our southeast counties took into account the extrapolation from what was going on at this point. You can see a boundary just north of the storms. So you can see there's a split occurring now, and the left mover is going to go from about 200 degrees at 43 knots, which basically parallels and is about the same speed as the ID method left mover. And of course you can see the right mover has split off and looks very nice right now, and we're going to track that one now, and that basically parallels the ID motion a little slower than the forecast from the RUC 40, but also goes to the east-northeast and very intense storm that went on to produce some strong tornadoes. Now, that was a great example of where it worked well for both right and left movers, and there's lots of examples where it works very well for these isolated storms. But I'm going to spend most of my time looking at the complications that occur. Now, storm propagation is not always completely dominated by internal dynamics, as we know. There's gust front propagation, we have boundary layer convergence features or pre-existing boundaries that the storms interact with. Different types of storm mergers, even in the warm sector. Topography can affect it. And also, I'm going to look at some non-standard shear profiles that can create issues. So the ones that have stars next to them are examples I'm going to show. Gust front propagation, we get new cell development along a well-defined gust front, or where the gust front merges with the moving front, which is really a hybrid of two different types of propagation. And the new cells merge with the main supercell. This usually results in a propagation farther right compared to the ID method, and it's a lot of times slower. Here's the example from the Zeitler and Bunker's 2005 NWA article, where you have the supercell that's moving due east, pretty much following what you would expect from an ID method. However, you have new cells developing along the flanking line that are going to merge with the updraft area of the storm. As that occurs, the effective updraft and mesocyclone start propagating to the southeast, which ends up new motion to the southeast, which is a little bit slower than the previous motion, and obviously to the right of that motion. Obviously, Warren-Jet implications here. You're tracking a supercell that looks pretty persistent, but you're getting these new cells developing, going into the updraft area. You have to be concerned about this movement to the right. An example from our area, we had 13 May 2009, East Central Kansas. Severe risk for parts of southern and eastern Kansas. Winds in the warm sector were veered, which was one of the reasons it was a severe watch from 210 to 220. So we had 30 to 40 knots of 0 to 6 kilometer bulk shear, plenty for supercells, and about 15 to 20 from 0 to 1 kilometer bulk shear. Not super, but enough for low-level mesocyclones. Maybe will they persist? That was a question. As the time went on, I'll show you the loop here, but the initial intensifying storm that we're going to look at moved from about 255 degrees to 35 knots. The supercell estimate from the ID method gave 270 at 30 to 40, but the storm was forming along a cold front, and what we'll see is where the storm gust front interacted with the cold front, new cells developed and merged with the initial intense storm, and our resultant supercell moved from 300 to 310 at about 25 knots, so well to the right and slower than our estimates from the ID method. Supercell produced two brief tornadoes. So on the following slide, just showing the environment again, 0 to 6 kilometer bulk shear vectors in yellow, 0 to 1 kilometer bulk shear magnitude in dash cyan, and the 0 to 1 kilometer shear was not all that large because of the veered surface winds. So here's our cold front, basically from east of Topeka. Here's Lawrence here, east of Topeka to just west of Emporia. This is Emporia, to east of Wichita down here. So here's the cold front. Out ahead of the cold front, we have bulk shear vectors in yellow of about 35 to 40 knots, and we have 0 to 1 kilometer shear in the dash cyan contours from 20 to about 15 knots, so 15 to 20 knots. So obviously an environment where a supercell can form, low-level shear is not tremendous, but we could be concerned a little bit about tornadoes at least. Radar loop is going to look at almost a 3-hour time sequence pretty quickly. And on that loop, we'll have the ID right mover supercell forecast estimate overlaid as yellow wind barbs. So here is our front, our cold front, showing up as this weak echoes along here. The storm we're going to follow is this one northwest of Emporia at this time. You can see the ID method right movers vector on here as 30 to 40 knots out ahead of the cold front, basically due east. We're going to follow this storm through time. So the storm's intensifying, and about at this time it was intense enough that a warning needed to be issued. And a pure extrapolation warning, of course, would take it into this county here, take the eastern part of Lyon County here into Osage County here. And would that have been a good move? Well, we know the environment is such that supercells are certainly a possibility, and it's starting to take on a very organized shape here. And we also know it's forming along a boundary. So a pure east-northeast motion at this point for extrapolation would not work very well. So you can see it becoming a supercell now. It's still being tracked okay by our initial estimate. But now really we have to recognize that it's moving more east and now paralleling essentially the ID method estimates. And we're seeing new cells developing on the southwest side as this gust front interacts with the existing cold front. And now our weak echo region, obviously the main updraft area, is moving southeast. And now we're tracking it more from about 300 degrees as opposed to 270. And we have a pretty good looking storm here, and we're getting a nice appendage in the weak echo region down here. And right now, at the time of the best hook, one volume scan later, we have a brief tornado touchdown just east of New Strawn, northeast of Burlington. And a chopper from the Kansas City area happened to be in the area and took a picture of this 30 to 40-second tornado that occurred there. And another tornado occurred about there along the Anderson-Coffee County line. And then basically the storm became more linear and it turned into a squall line as opposed to a supercell. But obviously a challenging polygon situation, as both the gust front and the ease with which new cells were developing along the gust front and the fact that it was interacting with a cold front resulted in new cell growth on the southwest side of the storm, which fed into the updraft area, resulted in a propagation well to the right of the ID method. So the initial storm motion for this case was to the east-northeast, took on supercell characteristics. It moved east, paralleling the ID estimate. As we had convergence along the gust front and cold front, new cell development merged with that supercell from the southwest. And so the resultant motion was to the southeast, well to the right of the ID method, and much slower, well, no, and somewhat slower. So when you see situations like this, be prepared for movement to the right of the ID estimates when you have new cells developing. And it obviously leads to challenging polygonology, difficult to anticipate eventual direction. Just be aware that this occurs and allow for some uncertainty in drawing those polygons. So another boundary layer convergence feature, this will be where a different type of front, perhaps a stationary front. And when we talk about this, it's an existing boundary of some kind pre-existing the convection. We have focus forcing for ascent with new developing cells merging with the original storm. This can often result in a slower movement compared to the ID method and possibly a different direction. So this is the example out of the 2005 Zeitler and Bunkers paper. And we had a northwest-southeast oriented stationary boundary with a supercell interacting with it, and the supercell would have normally moved to the northeast following the ID method without its interaction with that boundary. However, we have focus forcing for ascent in that area and new cell growth along the boundary, which then feeds into the southwest side of the storm. And the essential factor is that propagation offsets advection in this case, and you have a storm that's basically tied to the boundary and a supercell complex. It may not be completely continuous storm, it may be more discrete supercell, but a supercell or a series of mesocyclones is tied to the boundary itself. And the case that I'm going to show for this is pre-West, pre-AWEPS archiver. From 13 June 2001 in north central Kansas. We had storms developing along a northeast to southwest oriented boundary over north central Kansas. The winds in that area in the warm sector from the south-southeast at 15 to 25 knots, and I'll show you the Concordia observation on the following plot. Zero-Z soundings from all surrounding radar sites suggested a northeast supercell motion of 20 to 30 knots using the ID method. And we had continual redevelopment of new cells along the boundary, which merged with the main storm, and this resulted in a nearly stationary supercell. It only moved northeast at 5 to 10 knots, whereas the ID method would have suggested 20 to 30 knots to the northeast. And so it stayed for a long time over a small area of northeastern Republic County. And we had tornado warnings out for that area for a long time that it continued into south central, southeast Nebraska. So these are just thrown up here to show the ID method predicted supercell motion from surrounding RAOB sites. This is Dodge City well to the southwest, see northeast 25 to 30. This is Topeka to the southeast, which is also northeast at about 20. This is Omaha to the northeast, which would give us 20 to 30 to the northeast, and then North Platte to the northwest, northeast or east-northeast at about 20 to 25. We're going to look at a 3-hour reflectivity loop quickly. With overlaid on that is the surface plot, and also an altimeter setting every 0.5 inches, theta E every 3K, and that's a dashed red. And this was before, like I said, the AWEPS archiver in the west, so it was created in digital atmosphere. So here is the storms we're going to be looking at in north central Kansas. This is the Concordia observation south-southeast at 15 knots. And the boundary, as the dashed theta E contours would show, is oriented from southwest to northeast across that area. So the winds in the warm sector are basically oriented almost perpendicular to the boundary orientation. And as we look ahead through time, we have now the storm starting to take on supercell characteristics across northeastern Republic County. which is this county right here. And we have a nice weak echo region in that area, and we just get new cells developing in the area to the north of Concordia, merging with the southwest side of that storm, resulting in very slow motion of that supercell to the northeast, and tornado warnings that went on for a long period of time for that county, and then continued with this slow moving supercell into south central southeast Nebraska. So what are the implications from this case? Well, unlike the previous ones where the storm motion could easily be out of the polygons that you would draw quickly, it's not quite as big of a deal because this motion, in this case at least, was to the northeast as well. So we had the polygon oriented in the right direction. It's just that we had to keep reissuing because it kept going slower than maybe we would have expected initially. So the implication is the warning may expire before the movement out of the warned area due to slow motion. But it also could be, although not in this case, that you could have a significantly different direction than the ID method would give. So something to watch out for. And it's an example where the ID method will not give you a good storm motion estimate. And these are tornadoes that were produced in a relatively small area over the course of 2 hours. So we've looked at propagation along boundaries, on gust fronts. We're going to look at mergers now that occur maybe in the warm sector, which still complicate factors. We know that mergers can be constructive or destructive, and that's hard to predict. Our main problems come about with intensification from constructive mergers, which occur occasionally. And a couple examples of that recently were Redding, Kansas, which is in our county warning area, where the environment didn't appear to support a really strong tornado and extreme radar signature, but two supercells merging resulted in a constructive merger and a F3 tornado that destroyed much of Redding, Kansas. The next day, Joplin, Missouri, more famous, obviously, two supercells merge in what looked to be a constructive merger, and we had a very violent tornado that went through Joplin, Missouri. Once again, it's hard to tell, but was that tornado, that supercell, much stronger than it would have been because of the merger of those two storms? But we're not going to be looking at that. We're going to be looking at what can happen when you have a warm sector merger that can complicate your warning for a supercell storm. So the example out of Zeitler and Bunkers here shows a supercell that merges with an ordinary cell, and after that merger the mode of the storm changes and it turns into a bow echo and accelerates to the southeast. I'm not going to be showing that type of example. I'll be showing one where a ordinary cell in the warm sector merges with a supercell and results in the development of the storm to the right. So this was from 6 April of 2006. It was a high-risk day with a narrow moist sector ahead of the dry line. We had straight-line hodographs initially, which resulted in splitting storms early on. Our main tornadic supercell was well behaved for quite a while. It moved from about 200 at 35 knots, producing a number of tornadoes, and which was in the same direction but a little slower than the ID method. And then a cell merger resulted in redevelopment of the updraft to the right or to the east in a northern tier of counties, which had complications for our existing polygon warning. I'm going to look at a radar loop from 2100 to 2245, so about an hour 45 minutes on the 6th of April. And we'll have overlaid on the radar loop a right mover supercell motion estimate, and it's overlaid in tan wind barbs. And there we have those, and that suggests a northeast or north-northeast motion of 35 to 40 knots. And the actual motion of this long track supercell was basically paralleled exactly the ID motion and was at 36 knots. So this storm produced tornadoes through here periodically, and one just west of Clay Center here, and it was well behaved and moving basically right along this extrapolation path. As it got east of Clay Center, a new cell developed just east of Clay Center and was moving due north at the time. And as it merged with the supercell, We now have the weak echo region well to the right of the extrapolated path, an appendage here, tornado now on the ground, and I'll show you the polygons that resulted and were challenging to begin with. And the tornado basically moved on up through the eastern part of Washington County, which is this county here. So I'm going to look at the same sequence now with the polygon for Washington County that was drawn. So here's the storm once again moving through Clay County. Here's Clay Center. Storm moving north. About this time, to get enough lead time for Washington County, since it's been a persistent tornadic supercell, with about 15 minutes of lead time, Polygon was put out in the previous volume scan, and it took it up through this portion of Washington County. Now this cell here, which you can see aloft as well, and is now moving north and is going to factor into this. We can see we're tracking the low-level mesocyclone, which is nicely behaved, moving north into the south-central portion of this polygon. However, this new merger here results in what we see here with the appendage now outside the polygon, mesocyclone outside the polygon, and a new polygon, sliver polygon, had to be issued for the eastern part of this county as the storm continued moving northeast. So we can look at this and say, yeah, this polygon was probably too narrow to begin with, given how far out it was issued ahead of when it was going to cross this border into this county. And that's true. But it does show an example of where you have a merger which can result in a redevelopment of the updraft region of a supercell storm outside of what you might have otherwise expected without that merger. And there are the tornadoes that occurred with that storm. So the implications are, it did a great job, the Bunker's ID method did a great job with the initial tornadic supercell motion. When we had a cell in the warm sector merge with a persistent supercell, that's where the problems began. And so with the resulting redevelopment to the east, it took it out of the initial polygon, and we had to draw a thin sliver polygon to the east of that initial one. And what that really means is we need to watch out for these potential mergers, even in the warm sector and even aloft. This one showed up at the surface well in advance of the merger. But sometimes these mergers basically show up aloft, and you're going to see them in 4 panels or all tilts, and that can give you a little bit of heads up that something might occur and maybe allow you to enlarge the polygon on that inflow updraft side of the storm if you're going to see a potential merger coming up. Another issue is this non-standard shear issue. Once again, the ID method is physically based, but it's derived from a statistical database. So it works well on average for isolated storms. However, anomalous shear profiles that fall, on the extremes of the database on which they were basing this study and this method are not always handled well because of that. And you can have rapid changes in those shear profiles. So we know that the mean wind and the bulk shear are utilized in order to come up with this left mover and right mover. And even when the shear profile in certain portions of that hodograph change, that mean wind and that bulk shear may not change. So I think cumulative shear may have some factor into this, and I've seen it occur occasionally where extreme low-level winds that don't really change the bulk shear vector or the mean wind vector can affect the motion of the supercell. Maybe the propagation aspect, the vertically directed pressure gradient forces, other things could be going on. Obviously, it occurs most frequently during the evening, and it coincides often with decreasing instability and decreasing storm depth. So this example is from 29 May 2008. We had a strong system with supercells moving to the east-northeast across western into central Kansas. During the evening, a very significant low-level jet and low-level shear increase occurred, and the long-lived supercell started producing the strong tornadoes. It produced some weaker tornadoes early on, but then it started producing stronger, longer-lasting tornadoes. At the same time, the storm depth increased, and this was probably between 0.1 and 0.2 Z time frame. And the northern Kansas supercell, for a long time, was moving from 260 at 34 knots. ID method was similar, gave 250 at 35 to 40. But as it started producing the strong tornadoes, as the shear really ramped up in the low levels, it curved to the northeast and was moving from 220 at 34. And the ID method from the RUC 40 was still 250 at 35 to 40. So there's quite a deviation from what the ID method was thinking it still should be for that same supercell, but quite a bit changed there. And this is a graphic from Fisher and Davies' 2010 NWA Electronic Digest article on nocturnal supercells. And we'll look at this northern supercell track. This is the one I'm talking about in this case. This was for June 11th, 2008 supercell. And you can see the track was basically east-northeast for a long period of time, 01 to 02Z. The low-level jet cranked up big time. The storm turned to the northeast and started producing the stronger, longer-lived tornadoes. Only tornadoes that were strong are plotted on these tracks. So here's your radar loop, basically a 4-hour loop. Every 15 minutes on the radar with the RUC 40 internal dynamics method, right mover vectors on it. It was pretty good for a long time, but then as the low-level jet strengthened near sunset, the storm really deviated to the left and produced the strongest tornadoes and the long-track tornadoes. So here's the storm we're going to be following. It's a long way from Hastings. This is the radar from Hastings. It's a long way, so it doesn't look all that great at this point from this radar, but it looked better from Goodland at this time. You can see our ID method right mover vectors was from about 250 at 35 here. And the storm was basically paralleling a nice track from about 260 at 34 knots, and now around 01 to 02Z, it started deviating from that track, started moving more northeast, and here we move much more northeast, and there it's about from 210 at this point moving northeast, and then it hooked up again and went across our northwesternmost county there. And you can see that if you're expecting, based on persistent what's gone on, as well as from what the ID method would give you as a prediction for this storm, that it wasn't going to go very well. And let's look at the large increase in low-level shear here. The 0 to 3 kilometer storm relative velocity went from about 400 to over 700 in a period of 3 hours during the evening. And these are the SPC mesoanalysis graphics. This is about approximate area where just south of where that storm went later on. And at 0Z, it's giving about 400 meters squared per second squared in that area. There's 2Z, and it's giving about 650, and there it's giving 750 by 03Z. So big increase in low-level shear during that time. I'm also going to show that on a 6 and 9 hour forecast from the RUC, showing the area just south of the supercell track, looking at the hodograph there. This also shows a large increase in low-level shear and storm relative helicity with little change in storm motion. So note the storm motion and the resulting storm relative helicity is not calculated in AWIPS using the ID method. But in this case, the direction was the same as the ID method, just a little slower. So here's the 6-hour forecast valid 0Z on 30 May. And you can see storm relative helicity for this default storm motion of about 382 meters squared per second squared at this point. And it's to the east-northeast at about, I guess, 29 knots. And there, it hasn't changed much in terms of the forecast storm motion, and also similar to the ID bunkers method, only a little slower, same direction. But the storm relative helicity in these low-level winds in the lowest 2 kilometers increased greatly, and so the storm relative helicity went up 300 meters squared per second squared over the course of 3 hours. So the warning challenge from this storm was, with tornadoes occurring, we wanted significant lead time to the western county warning area border. And it's still an impressive supercell, and the ID method continued the east-northeast track. So the storm began turning more northeast, but the warning forecaster expected a return to more east-northeast, and that didn't happen and went even more northeast. So you can see or imagine potential problems here, and you'll see them coming up. So this is a track over the last 4 volume scans of the hook area of this storm, moving to the northeast, north of the ID method at this point. And the warning forecaster issued the warning at this time based on these extrapolation from the last 4 volume scans. And this person expected it to maybe turn a little more east again if it was really going to continue to be tornadic. Well, that wasn't a very good reasoning, and we'll see why coming up shortly. Storm is now moving from 210, or the mesocyclone is moving from 210. And at this point, we get a call from the Dow of a funnel cloud on the Republic-Jewell County border, basically right in here. And a new warning was issued for the northern part of this county, which is outside. Essentially, the tornado never touched down in the initial polygon. So the storm motion changed radically, and really pure extrapolation would have been better, but still not good enough in that case to handle the motion that this storm went. So I guess in this case it's hard to say exactly what to do. Just recognize that when you have anomalous extreme shear profiles, that the ID method may not be all that good, and you're going to have to allow for maybe a little more uncertainty, especially if things are starting to change at all. And then the storm moved northeast, producing a long track tornado across Republic County, which continued on up into southern Nebraska. So the takeaways from this case: ID method is not always a reasonable estimate, even for an isolated storm. Significant changes in the hodograph and the cumulative shear may not be reflected in a significant change in the internal dynamic supercell motion estimate. So look out for this, particularly when you have a low-level wind shear increase, particularly during the evening, already in association with an already strong system. And there are the tornadoes that occurred. These weaker ones were earlier on as the storm was moving to the east-northeast. So the wrap-up now. Polygonology. We put together the meteorological factors and the non-meteorological factors to come up with the best initial and follow-up polygons possible. We try to minimize tornado warnings for counties that are just touched by polygons but not truly threatened by the tornado. And we try to minimize the area overlap when significant overlap is unnecessary. Why warn the same area twice if you don't need to? Also try to minimize warning multiple times for the same storm for the same county. Now, sometimes with long-lived supercells that are moving fast, you can move them through a county pretty quickly and issue one warning for that county and everything works out pretty good. Obviously, there are times you simply can't do that, so you do what you have to do. So just going through the technique for tracking supercells for warnings, you need to know what the ID method is going to give you. For isolated supercells, it's a good reasonable first guess in the direction that is isolated developing supercell will move. You must have left and right moving bunkers ID vectors overlaid on your warn gen panel. You need to know what those are. You need to know if they're changing. It's a good first guess in quite a few situations. You have to recognize where ID method is good and where it's not. Look out for and adjust based on new cell development along a gust front from the supercell, repeated new cell development along a previously existing convergence boundary with potential mergers, other mergers that may occur out in the warm sector, these anomalous shear profiles, elevated storms and shallow storms which kind of fall on the edges of the ID bunkers method statistics. Once you have your estimate, your best initial estimate for this storm, you have to consider other things. You modify your polygon appropriately for what you expect the storm motion to be. You have to factor in uncertainties, obviously. You choose your duration of the warning based on your storm type. Pulse storms are different than supercells and bow echoes. Your threat and the workload. If you have steady state storms and you don't have very many people in the office, you probably can get by and should be doing longer warnings so you don't have to make those warning decisions as frequently and maybe overlook something that you shouldn't be overlooking. You also base it on the potential for rewarning for the same geographic entity. If you don't have to issue multiple times for the same county, don't. You pull in the default back end of the polygon to the back end of the storm because the default is well behind the dot that you're using for tracking the storm. And for fast-moving storms especially, that's way behind where the thread is. You pull in the default far end of the polygon closer to the tip of your Warringen extrapolation arrow if you have good extrapolation. If you don't, it's trickier. And if you have counties that are barely clipped by the polygon, you have to ask yourself, is there a significant threat for that warning, a very low probability event for that clipped area? And if the answer is yes, or at least in the near future, is that clipped area well downstream, then maybe don't clip that county. Take care of it later if you need to when the certainty is greater, or don't clip it because you're warning tornado and you might get 1 inch hail, maybe barely, in that clipped area. Turn off your image. This is always a good idea. With the low reflectivity values, it can sometimes overlay things and you don't see your W's or your hatched areas. Turn off the image to look for accidentally clipped counties. And if you do pull out counties, make sure you click redraw to warned hatched area to ensure you have what you want before you create your text. As a final example of just going through this process, this is from 3 April 2011. This was an example with a high LFC, high LCL environment. We had sufficient deep layer shear for supercells. The initial storm developed, and we have to ask which way will it go, what areas to warn. So here's the sounding from Topeka from a couple hours before our warning experiment here. It's showing a very high LFC, LCL environment, relatively dry, low layers. The directional shear is not all that great in the sounding, but we do have 60 knots at 20,000 feet, so good deep layer shear here. On this panel here of environmental data, we have the right-moving supercell vectors at 22Z from the rock analysis showing east-northeast at about 45 knots. And we have the 0.6 kilometer bulk shear magnitude on here as the contours in green, and that's about 45 to 60 knots in the area that we're going to be concerned with. So definitely a supercell type environment. The cell we're going to watch here is forming behind this cold front, which is sagging slowly southeastward. And we're going to track this storm over the next few volume scans and see what happens. Storm is moving to the northeast. Boundary is moving to the southeast. And right about this time, it looks like the storm is have 70 dBz up to about 25,000 feet. It's looking to be severe at this point, and you better issue a warning. And the track, approximately at this point, would give us this, which takes it to the northeast, and the default polygon is overlaid from Warringen on this. So you can next draw in, if you have a good track on it, and I'm not sure we do at this point because we only have like 4 volume scans to track it. But if you did, you could draw in this far end of the polygon into the tip of the extrapolation arrow, kind of. This is about where it'd be at 0Z. But are we done now? Is this all we need? Well, we know it's a supercell type environment, and so the bunker's ID method would give east-northeast at about 260 at 45 knots, and so maybe we better account for the fact that this thing could turn into a supercell rather quickly. If we do that, we can draw the right end of the polygon down to the south, and that would probably, in parallel, kind of bunker's ID method vectors. And that may take care of it. But we also know that this boundary here is sagging to the southeast, and it's possible that at least some part of the propagation of this storm could be tied to the fact that this thing is moving southeast. So let's maybe just, for uncertainty's sake, draw it slightly further south, due east basically, to account for that potential unknown of whether this propagation is going to have anything to do with this boundary here. So now we can put on our counties, and we see that it clips a couple counties. This one is not hatched with a W in it, so that one looks okay. But Shawnee County here has a very small hatched area in northwest and west central parts of the county. Now that's at 45 minutes out essentially, and we're not certain. We don't have great certainty about things at this point. So why, warn for this tiny area of this county this far out? We know we can get it downstream if it continues to go and persists, and we can get it in the next warning as long as we're proactive and get some decent lead time as the storm is moving through this current polygon. So that's what our polygon would look like at this point. So let's see what actually happens in time. I put the tan lines here as the northern and southern extent of our polygon that we decided on, and this dashed orange line is the southern extent of what the default extrapolation polygon would have been here. So let's see what happens with time. Storm is moving northeast, east-northeast, and the echoes, now the appendage is extending beyond to the south of where our pure extrapolation polygon would be, and it's only been 10 to 15 minutes from when we issued the warning, about 15 minutes. And now it's well south, and damaging winds are occurring along this area here, outside of where the initial polygon would have been. And really damaging winds extending now a little bit south of the actual reflectivity area here, and moving basically due east at this point. Now we would have had to stick out that downstream warning for southern Jackson here and Shawnee County well here, well to the west, when it was obvious it was going to persist and stay strong. But I'm not showing that at this point. So you can see right here that using our knowledge of what supercell, that the environment is a supercell environment, that we are warning early, that the ID method would take it to the east-northeast from about 260 degrees, and we also had maybe a boundary interaction of some type affecting propagation, that we had to enlarge that polygon due to uncertainty in the motion of that storm. And by doing so, we encompassed the threats from that storm pretty well and did a pretty good job of warning for this storm. And this is just showing the southern extent of that supercell and the time sequence of reflectivity from that supercell, showing what it did. And then we had several more supercells that did almost exactly the same thing. Initially, they'd start up moving to the northeast, and then as they became supercells and were tied to the boundary, they essentially moved due east through time, somewhat paralleling, pretty close to paralleling the ID method. So the wrap up, once again, drawing good polygons can obviously be very challenging at times. We are trying to make a forecast, not a pure extrapolation, but a forecast for the threat 30 to 60 minutes into the future. We are factoring in meteorological and non-meteorological factors when we're drawing these polygons, recognizing that good polygons go well beyond pure extrapolation. We have to be cognizant of multiple things when we're thinking about meteorological factors. And also recognizing, very importantly, that many people are still being warned by county and perhaps overwarned because of that, and we must judiciously consider when we're drawing our polygons. Judiciously consider whether we need to or not need to clip a small portion of a county with a polygon. And that is the end of the presentation. Hopefully this helped review some things associated with maybe the Bunker's ID method, and I encourage you to go through the training that's online. From that, read the papers, go through the training if you want to know more. I also want to encourage you to think about all these things as you're going through practice West cases, as you're working your events this year. After you've done the event, look at your polygons. Could I have anticipated that this storm was going to move outside of that polygon? What could I have seen? Could I have seen that merger that was going to happen? Didn't I factor in that boundary that was still there that I should have maybe factored in? And think about that and learn as you go along. And I think we can make better polygons and more judiciously determine when certain counties need to be included and when they don't. Thank you for listening.